Okay, welcome Caesar and Jesus and Jordan and Ralph and Victor. Um, and welcome Bradley. This is, we're getting towards the end. So we only have really a couple weeks left and then we're finished with linear algebra. So I hope you're getting something important out of the course. You should be, because there's a lot of information that you'll use in your upper division work. What I'm gonna do is I'm gonna share my screen so that we can talk about the agenda for today. All right, so the plan today, as usual, is we'll start out with Q&A. And I want to mention, while we're talking, I'm going to let this be a first come, first serve in terms of deciding what your presentation is going to be. So if you post it in the chat box, and then no one else can do that one. So Caesar and Vardo, are you doing voting paradoxes? Great, great. Okay. Just a note, by the way, I personally worked on this and changed the election a bit a few years back. So it's a long story. And it helps to know math when people are looking to figure out how to best figure out voting things. So we got quantum mechanics with Jacob Bradley. We got Victor is doing image compression with Ralph. And again, it is important that everyone has a partner. Yeah, that's not allowed to do this alone. So again, you can be two, and if everyone's got twos, if we have a total of 8, because 4 two-person partners, then the last person can join a group, and hopefully all of you will be okay adding in the last person. Okay. Yeah, so hopefully Jason will respond. I'll have to check to see whether he sends me emails via his private email or his college email. Hopefully he looks at his college email. That's always the issue sometimes. So let me tell you the plan. Today, there's really nothing new today. That's the good news. Nothing specifically new. What's new is the way of looking at it, just like last time, is we'll talk about a subspace, which we've already talked about. We had a definition of subspace. It's exactly the same definition that we had before, except now we're going to view it as a subspace of a general vector space instead of a subspace of a vector space in Rn. Same thing. We'll talk about what it means if we have a subspace. How do you find a basis, or what is a basis for a subspace? Again, the same definition will hold, but I'll repeat the definition so that you can remind of it. This is actually a good review for the final in a way, because all this stuff was really important from before. Then we'll talk about dimension. So how do you find the dimension of a subspace? And basically it's the same thing as what we did before. So that's the good news. Today's kind of a review day, even though you've never seen any examples that we're going to do before. I mean, because all you had was Rn, but all the ideas still work. Okay, then we're going to get into the next section, and that's on sums and intersections. So that's a special case, but a really important one, is that if you have 2 subspaces and you want to say, well, what if I take all the sums of the subspaces? And the good news is that's going to be a subspace. And what if I take the intersection of the 2 subspaces? And the good news is that's also a subspace. Then we'll talk about a direct sum, which is just a special case of the regular sum. And that is the plan. I do want to note something, because I want to make sure that you're not confused when you get to the homework that's due on Monday. And that is the author got lazy at the end of the book. That happens sometimes, but it's a free book, so you can't get mad at him, right? So there were no exercises for the last the last part, half of chapter 9. So what I did, because I'm not that lazy, is I created exercises for that last half. So you will see on the syllabus, there's a link to the collection of exercises that I created. When you click on that link, that gives you all of the exercises for the rest of chapter 9. You only need to do the ones for the section we're in, whatever day we're in it. So just let you know that the exercises from the last half of today to the end of the class, which is only a couple more days, are all written by me, and they're not in the book. And that's because the book didn't have them. I was like, what? How could you not have exercises? There's regular sections, they're not even special sections. So I don't know. But anyway, so if you have any questions about the exercises, there shouldn't be any issue on getting to the exercises. You just click and then it'll show up. You could either click and have it show up directly in Canvas, or you can click the other one. There's like 2 links in the same spot, and that will download a file. It might have made a Word document, I don't remember. Maybe a Canvas document. So that is the plan for today. And again, I wanted to give you that heads up about the exercises. So are there any questions? Could be about homework or anything else, or the presentations.
Do you mind going over problem 4 and 9.3?
9.3, number 4. Okay, it takes a moment for me to get to it. Oh, good. I got lucky. I happened to be in 9.3. I have to choose one. So I'm in 9.3. Let me get to number 4. Just a second. Okay, so here's 9.3, number 4. It says, find a basis in P3. And P3, by the way, is a space of all polynomials of degree 3 or less. We've had the PNs before. For the subspace, the span of 1 plus x minus x squared plus x cubed, and then I'll let you read the rest. Okay, and then if the above 3 vectors do not yield a basis, okay, exhibit one of them as a linear combination of the others. Okay. Any questions on the question?
No.
Okay, so we're looking at the span of this, and we want to find a basis. So basically, it's a little weird because they don't talk about bases, and I understand when you're asking this until the next section, which I'm going to be talking about today. So it's a good thing you asked. Again, the extra is a little interesting in chapter 9. Like there's none after section 4. But it's the same definition that we've had before. Okay, and we want to find a basis in P3 for this subspace. Okay, so what do we need to do? Notice that there's 4 vectors. It might be all of P3. We don't know yet.
We need to see if they're linearly independent.
Yeah, so we need to see if they're linearly independent. And what we can do, let me pop in an equation, is we can go, I'm going to use A, B, C, and D, easier to type. A times 1 plus x minus x squared. Again, always go right for the definition. Plus x cubed plus b times 1 plus 2x plus 3x cubed plus c times -1 plus 3x plus 5x squared plus 7x cubed, and then plus d 1 plus 6x plus 4x squared plus 11x cubed equals 0. Okay, so when you want to find out if vectors are linearly independent, then this is what you always do, is you write down a constant times the first plus a different constant times the second plus a different constant times the third plus a different constant times the fourth equals 0, if there's 4 of them. Any questions? Any questions at all on that? Does that make sense? First step?
Yes.
Okay, what's the next step?
I would say multiply through.
Yeah. Is it okay if I do a few steps at once? Otherwise, it's a lot of typing.
Yeah, go for it.
If I kind of walk you through what I'm thinking as I go, and if you don't understand, let me know. So what I'm gonna do is I'm gonna multiply through. I'm gonna combine like terms and look at the coefficients. Does that make some sense? So in particular, we're going to have an A plus B minus C plus D equals 0. That'll be the first equation, right? Does that make sense?
Yeah.
Looking at the constant coefficient. We're going to have a AX plus 2BX plus 3CX plus 6DX equals 0. But I can divide by X, and I can say A plus 2B plus 3C plus 6D equals 0. Does that make sense?
Yes.
So I'm going to have 4 equations, 4 unknowns, and you better all know what to do when you have 4 linear equations and 4 unknowns. What do we make?
A matrix.
A matrix. So let's do that. So pop in a matrix. This is going to be a 4 by 4 matrix. Oops, here. There we go. Okay, and the first one is going to be 1, 1, negative 1, 1. The second row will be 1, 2, 3, 6. The third row will be negative 1, 0, 5, 4. And the last row will be 1, 3, 7, 11. Does that make total sense?
Yes.
Okay. So typically, and no different with this, when you're solving a system like this and it's a homogeneous system, what's the next step?
RAF it.
Yeah. And what did I tell you the best way of RREFing something like this is?
With a computer.
Absolutely. Yeah. I don't want to do it by hand. Did any of you do it? Any of you have it on a piece of paper? Because I haven't done it physically, but any of you have it? You can read it off to me.
Yeah, I have it.
Okay, so you've gotten that far. Sounds like you did a lot. Okay, so
So
somewhere
I
you
got
So let me get to it. Let me go to insert a matrix. Okay, so what'd you get for the first row? Sure, 1 to start.
1, 0, negative 5, negative 4.
Okay, next.
And then 0, 1, 4, 5.
And then
The
next.
last 2 rows are all zeros.
Right, that I knew. Given the fact there were 2 free variables, that was obvious. Okay, any questions so far?
I'm still a little bit confused about the last 3 rows on the original matrix.
Okay, so the 1, 2, 3, 6, those are the coefficients in front of the x's. Do you see that? The first polynomials, x is just 1x, the second is 2x, the third is 3x, and the fourth is 6x. That's the 1, 2, 3, 6. Does that make sense?
Yeah.
Nothing tricky. And the next row is the x squared coefficients. And that's just how system of equations work, is you combine like terms and then you put them in a matrix. Okay, any other questions on that? Okay, so now what's important here is notice that A and B are the pivot columns. Is that clear? And then C and D are the free variables. Is that clear? Any questions on that? Okay, we've been doing that for a while, so hopefully that should be clear. All right, so what that tells us in particular, again, let's read the question again. And if the above vectors do not yield a basis, which we know they don't, because a basis of P3 needs 4 linearly independent vectors, and we only have 2. Okay, so we know that we can let the first 2 be there. So let's do that. So we need to have our basis is, well, we can take the first 2. And let me write that in. Typing always takes time. Okay, so the first one is just going to be 1 plus x minus x squared, and then plus x cubed. Is that clear? That that's our first basis vector?
Yes.
The second will be 1 plus 2x plus 3x cubed. Is that clear? How many more do we need?
We need at least 2 more.
Not at least, we need exactly 2 more. Is that clear?
Yeah.
It won't be 3 more because that would be too many. So P3 has exactly 4 polynomials as basis vectors. Okay, so I think the easiest way is, I know this sounds weird, but write down some really easy polynomials and hope you get lucky. And the reason for that is you usually get lucky. So how about 1 and x? Any questions on that so far? Right? We're not guaranteed this will work, but it usually does. Any questions on that? Okay, then what I can do is I can take this original matrix and adjust. And I can put 1 and x. In fact, I'm gonna do it a little differently because it's easier. It's not really any different because it's a list. But if I put 1 comma x first, then life might be a little easier for me. Because the idea here is that that makes my first row 1, 0, 0, 0. And the second row will be 0, 1, 0, 0. Because the first one is 1, the second one's x, and that's the corresponding vectors. Okay, and then the third row will be 1, 1, negative 1, 1. And the fourth will be 1, 2, 0, 3. Any questions on that? Is that totally clear?
Yeah.
Okay, here's, yeah, does that make
makes
sense? About 13, sorry. Any questions? All right, I could use a computer RREF this one, but I don't need to because I could take this first row and just get rid of the one there, and I get rid of the one there. I could take the second row and get rid of the 1 here and the 2 here. And what's important? Why is that good?
It's diagonal matrix.
Yeah, and what's the determinant?
-3.
-3.
Right, but more importantly, not 0.
Yeah.
So it has non-zero determinant. So they are linearly independent. So that means it really is a basis. Okay. And I didn't use magic to write 1 and x. What I used is I crossed my fingers and hoped it worked. And if it didn't, then I'd maybe try 1 and x squared and see if that worked. And you're eventually going to get it.
That's clever though. I didn't even think of trying that.
Yeah, that's the easiest way. I mean, there's other ways too. Again, I'm not saying this is the only way to do it, but I think this is, don't you agree this is the easiest?
Yeah, definitely.
Try the easiest possible and hope, cross your fingers and hope it works. If it doesn't, you just try a different one. But I'd say 9 out of 10 times, maybe even more than that, the easy things are going to work. Okay. Any questions at all on this problem? Okay. And if they're linear independent, by the way, it's a basis. That was part of TFE. Any other questions? Okay, if there's no more questions, we're going to get into the new material. New in quotes, because really we're not doing anything new today. So I'm going to start out with, again, a word we've already had, but we only had it when we were looking at vectors in Rn. Now we have it when we're looking at any vectors, and it's exactly the same. So let me read out the definition. So let V be a vector space, and let W be a subset of V. Okay. By the way, if you put the little equal thing or the horizontal thing below, that means W is allowed to be equal to V2. Could be V, it could be smaller than V, but it's a subset. Okay, then W is a subspace. So it's a subspace of V if AW1 plus BW2 is in W for all scalars A and B and all vectors W1 and W2 in W. Okay. So that's interesting. That's the definition. The funny thing, the last book I used for this class, it used the note as a definition, and then it used the definition as the note. So it doesn't matter. You can go either way. They're equivalent. And that is, if you want to check whether W is a subspace of V, then you can just do 1 and 2 that we had before a long time ago. And that is add 2 vectors, see if you're still in W, multiply a vector by a constant, and see if you're still in W. Any questions at all on the definition of a subspace before we do some examples?
Is a subspace also a vector space?
So, good question. It doesn't say so here, right? But take a look at the next theorem. Wait, is it the next one? No, it's, let's see. Yeah, so there it is. It is next theorem. So the next theorem is yes. Does that make sense?
Yeah.
So you're ahead of me, but that's okay. So the answer is yes, and we'll get to it in very shortly. But I want to do I want to do an example first because I think it helps to see examples. So here's an example. Okay, let V be the space of all functions. Okay, and I'm going to keep it easy. When I say functions, I mean from R1 to R1. So not multivariable functions or anything like that. Just good old fashioned functions that you're used to from like first quarter calculus type of stuff. Okay, and W be the solution to the differential equation. Y double prime plus 2y minus 1 equals 0. Okay, now I'm going to tell you that there are actually an infinite number of solutions to this differential equation. Why might you guess that thinking calculus now? Any thoughts? Oh, you know what? Sorry, I made a mistake. No -1. That's better. Why might you guess that, thinking calculus?
If you were to integrate, you would have to put a plus C.
Exactly.
Infinite number of them.
Yeah. So you're going to have a plus C when you integrate. So there's going to be a lot of solutions. So the question is a set of all possible solutions to this differential equation a subspace?
Wait, wouldn't you need to have two constants? Because it's a double prime, so you would have to
Absolutely.
integrate twice.
Right. So guess what? If one constant gives you an infinite number of solutions, how many does two constants give you?
A second
bigger
degree of
infinite?
infinity.
An infinite number of solutions. Okay. You're going to learn next quarter that the dimension of the subspace is equal to 2 because of what you just said. There's going to be two constants going on. But you don't have to know that this quarter, but you'll learn about that next quarter. Okay. Do you believe it at least?
Yeah.
Okay. But now, how do we know that this is actually a subspace? What do we have to do?
Check to see if it's closed under addition.
Yeah, addition and
Scalar multiplication.
scalar multiplication. So here's what we do. I'm going to let, how about f, because it's a function, and g be solutions. Okay, then f double prime plus 2f is equal to 0. Do you agree? Any questions on that? And g double prime plus 2g is equal to 0. Do you agree? Isn't that what it means to be a solution? What do we have to check?
Check to see if they're the same.
Not the same.
If they're still in W.
When he's not
Or V.
there in W, but what's in W?
If we add them together, they need to have the right form.
Yeah, if we add them together, they have to be in W. So in particular, if I take f plus g and I double prime it and I add 2 times f plus g, what do I hope to get for it to be in W? It's easy, that's a hint.
0.
0. Because if it's 0, then it's a solution to the differential equation. Well, the good news is that the second derivative, we can split up the pluses. You can write that as f double prime plus g double prime. And then I can distribute the 2 through, plus 2f plus 2g. Is that clear? Now we're adding a bunch of functions, so I can use a commutative property. You're allowed to switch the order of pluses, and I could write that as f double prime plus 2f plus g double prime plus 2g. And what do I get? What's f double prime plus 2f?
F double prime plus 2F.
Yeah, what is it? The hint is look at the line above.
It's 0.
It's 0 because it says so. What's g double prime plus 2g?
Also 0.
That's also 0. And if you don't know what 0 plus 0 is, you got a big problem. Okay, so I just showed that if I add two functions that are both solutions of this differential equation, then that sum is also a solution. Now what do I have to check? In fact, I'm going to call this number 1. And what do I have to check now?
if it's closed under scalar multiplication.
Exactly. So I need to check KF double prime plus 2 times KF, where K is a constant. And what do I hope to get?
Zero again.
I hope to get 0, because if KF is a solution, then KF double prime plus 2 KF should be 0. So the good news is that you can always pull constants out of derivatives. So I can write that as K F double prime, and then plus, I can switch the 2 and the K times 2F. And now I could factor out the K, and I can write that as K times F double prime plus 2F. What's F double prime plus 2F?
That's K times 0.
Yeah, K times 0. And what's K times 0?
0.
0. So therefore, the W is a subspace. Any questions on this idea? By the way, do you think you'll ever use this idea?
Yeah.
Yeah, like pretty much half of next quarter. This is a major, major piece of next quarter. Next quarter, you'll prove it for general differential equations that are what's called linear differential equations. This quarter, I don't have to go there. That's Bruce's job. But I figure you can handle an example. You good with that? So that's a really important example. So now we can talk about solutions of these types of differential equations as being subspaces. Any questions on that? Any questions? Okay, how about this one? So here's another example. Let W be the subspace of 2 by 2 matrices such that the determinant of W is equal to 0. Is W a subspace? Any questions on this idea? Okay, what do I have to do?
See if it's closed under addition and scalar multiplication.
Yep. All right. Did we have, because we spent a whole chapter basically on determinants, right? Or maybe a whole very long section, but we spent a lot of time on determinants. Did we have the statement that if A and B have determinant 0 and you add them, you still get the determinant 0? Was that a fact? Was that a theorem?
Yeah.
One more guess?
No.
No, definitely was not a theorem we had, and there's a reason. The reason is because it's not right. So this one turns out not to be. And you've seen this before. If you have to prove something is true, then you have to go through all the, 1 and 2 with all the details. To show something's false, what do we have to do? What can we do?
Find one example that shows it's false.
Yeah, so let's just find an example. And it's an easy one. So let me grab an example. So how about one? I bet I should write A. A equals 1, 0, 0, 0. Do you all agree that that's in W?
Yeah.
Okay, so I can say that. I think it's in there somewhere. There it is. That's an element of W. But then let's let B be equal to 0, 0, 0, 1. Do y'all agree that's in W too? It's also in
Yes.
W? Take a determinant. Again, I'm trying to make it, you always want to do easy examples. No reason to go into some messy stuff. All right, what about A plus B?
You get 1, 0, 0, 1.
Yeah, we get that. Is that in W?
No.
It's not in W. I mean, that's the easiest determinant in the world, right? For the not, it's the identity. What's the determinant of A plus B?
1.
1. And that's not in W because the determinant must be 0. So this is not a subspace. Any questions? Any questions on these examples? Again, I gave you one that is, one that isn't. Any questions? By the way, if you tried scalar multiplication, do you think that would work? If the determinant of the matrix is 0 and you multiply by a constant, do you still get 0?
Yeah, for either A or B.
Yep. So that actually, there's no A and B in that case. It's just single matrix A. So if you take K times A, just in general, if the determinant is 0 and you multiply by a constant, the determinant is still 0. So had you tried number 2 first, you could have proven number true was correct, but number 1 is not correct. But to be a subspace, they both have to be correct. Any questions on that idea? Okay, so that's an example. Do you think, I'm not going to write this one down. What if it was, instead of the determinant was 0, what if the trace was 0? Would that be a subspace? Any guess?
I think it would.
Yeah, that one works actually. Traces are additive, determinants are not additive. Okay, I'm not going to do it because we only have so much time. Okay, now comes the theorem that was asked about, and now I can actually officially answer it, even though I kind of did already. And that is, if W is a subspace of V, then W is a vector space with the same sum and product defined by V. So your question was, is a subspace a vector space? And the answer is yes. Okay. I don't think I'm going to prove this. The first thing is, I guess number 1 and 6, that's what the definition of a subspace is. And the idea is all the rest of them are just true because it's all part of V. And I'll let you look at all the rest of them and realize that that it's just, there's nothing to say. Do you agree with me? Or do you trust me at least? Any questions on that? So subspaces are vector spaces. And that's the good news. That means we can use all the things we know about vector spaces. Just a note, to prove something is a vector space, if it is a subset of a subspace, of a vector space, then you don't have to prove all 10 of them. How many things you have to prove to show something's a vector space if it's a subset of a vector space?
2.
Yeah, just 2. And hopefully you'll agree that's a whole lot better than having to prove 10 things. Because that section where you had to prove all 10, that was a lot of writing. Do you agree? So the good news is most of the time when you have to show something is a vector space, it's sitting inside something you already know is a vector space, and you only have 2 things to show, and that's not hard. So I will let you know on the final exam. Do you think I'm going to ask you to prove something's a vector space by proving all 10 of them?
No, probably just a
Probably just,
couple of them.
yeah.
Which couple?
1 and 6 for sure.
Yeah, 1 and 6. Okay.
Mm.
And, there's a good chance I'll ask you to prove something's a subspace or something isn't. It's kind of the old, you decide what it is. And if it is, you have to prove it. If not, you have to prove it. So just note, that's how I'm going to be testing. Okay. Always good to note that. I'm not going to test you on all 10. Do you agree that would be just miserable? It would take like half the test.
Yeah.
And so I'm not going to do it. Okay. So here's another biggie, and this is easy also. The nice thing is all the theorems today are easy. So the span of a bunch of vectors in any vector space is a subspace of that vector space. How do you prove this? I'll prove this one because it's not that hard.
I was going to say take the span of a few vectors of a subspace and then see if they are closed under addition and scalar multiplication.
When we say take the span, what do you mean by that? Not quite take the span, because you don't take a span.
Check to see if something is in the span.
Yeah, so if you have two things in the span and you add them, you still have to have a thing in the span. What does it mean to be in the span of a set? Do you remember?
You can write them as a linear combination of vectors.
Yeah, exactly. Of those vectors, not just vectors, but those vectors. So the proof is, let's suppose I have C1, V1, and no more commas. Now it's plus, dot, 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 plus CK, VK. So suppose we have that vector. That's a vector in the span. Do y'all agree? All vectors look like that, right? And then I add another vector that's in the span. So let's do that. So that would be like a D1, V1 plus dot, 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 DK, VK. And the good news is, what can I do? Very basic math.
Combine like terms.
Exactly. I can combine like terms. So I can write it as parentheses C1 plus D1, V1 plus dot, 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 plus parentheses CK plus DK. VK. Do you agree I can do that? Okay, why is that enough?
Because it's still in the span.
Yeah, that's in the span because the definition of span is a number times V1 plus dot, 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 plus a number times VK. Well, C1 plus D1 is a number. CK plus DK is a number. All the middle ones are going to be numbers. Does that make sense? All right. But I should do this. I should call that number 1. And then I should go to number 2. And the good news, whoops, it wants 3. Come on. There. Okay. Now what do I have to show?
I mean, doesn't the definition itself already say it? Like show the proof of it for scalar multiplication?
Yeah, we have to do it. There's not much to it, but we got to do it. Yeah, definition doesn't do it. You got to, I mean, the definite does it with one step, but we got to do the step. So it says that if I take a constant, how about A for the constant, times something in the span, C1, V1 plus dot, 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 plus CK, VK. then I'm supposed to get something in the span. So what's the one step I got to do?
Distribute.
Yeah, that's all. Okay, but I do need distribute. So I get AC1 plus ... plus ACK. And that's it. We're done. Therefore, the span of V1 through VK is a subspace of V. That's the proof. I mean, it's one step, but you got to do the step. Any questions on that? Easy enough? Okay, and we'll be using that. I mean, I could write an example, and that just means just grab a couple vectors, say, now take the span. It's a subspace. There's not really much to say for examples. All right, so the next theorem is, let's suppose W is equal to the span of V1 through VK. And let's suppose that is a subset of V. And let's suppose we have U, which is a subset of V also, such that V1 through VK are all in U. Then W is in U. Okay. I guess I need to say, I think I copied it from the book, but the book might not have said it, but you need it. W in U, and U is a subspace. W. Then that means that W must be in U. I'm sorry, that U is a subspace of W. Sorry, W is in U. Okay, why is that? Why must that be true?
Because B1 to BK is in U and W is the span of B1 to BK.
Yeah, there's not much there, because if you have something in W, it's in the span, but anything in the span, if you add things and multiply by constants, then you're still in it. That's all that is. There's nothing really to say, so I think I'll just say it and move on. Okay, now we're going to get to the important definition. Okay, I wanted to get to the kind of less important, but they're in the book, so I figured I should cover them. And now we'll get to a biggie. And this you've seen before. You haven't seen it in general, but the definition doesn't change one bit. And that is, let's suppose you have S, which is equal to the set V1 through VK. And let's suppose that S spans V, and S is linearly independent. Then S is a basis for V. Okay, where have you seen this before?
A few months ago.
Yeah. Is it any different?
No.
Not at all. It's exactly the same definition. What's different is perspective, right? A couple months ago, V1 was always a vector in Rn. Okay, now V1 could be any interesting thing. Does that make sense? Okay, so what this says is, if you want to show something's a basis, then you have to show it's linear independent, and you have to show it spans. Any questions on the definition? So here's an example. And let S be the set 1 plus X, comma, X, comma, X squared. show that S is a basis for P2. Any questions on the question? Any questions? Okay, how do we go about it? What two things do we have to do?
We need to make sure they are linearly independent.
That's one thing. And what's the other thing?
To make sure it spans P2.
Exactly. Exactly. Because basis has two things. Linear independent and span. It doesn't matter which order you do it in. Okay, so maybe I'll start with linear independent. So let's do it. How do you show vectors are linearly independent?
If you have C1 times, let's say B1 plus C2, V2 plus C3, V3 equals 0.
Right. So C1 times V1 is 1 plus X plus C2 X plus C3 X squared equals 0. What's our goal? Our goal is to show the constants are all 0. Okay, well, when you have an equation with polynomials equals 0, what can we do? We did this in the question you had about homework.
We call combine terms.
Yeah.
You can combine like terms. Yeah, we're not going to need a matrix on this one, it turns out. I tried to pick an easy one. So then we get the equations. C1 equals 0. That's the only one with a constant. And then we also have C sub 2 is, sorry, C sub 1. Let's try one more time. C sub 1. That's in front of X on the first one, plus C sub 2 equals 0. And then if we look at the X squared term, that's just C sub 3, right? Any questions on that? What does that tell you about C1, C2, C3?
They're all the same and they all equal 0.
Yeah. Obviously, C1 and C3 are immediately 0 because it says so. But then if C1 is 0 and you have C1 plus C2 is 0, that's just C2 equals 0. So you don't need matrices for this. Do you agree? So this shows that all the constants are 0. So S is linearly independent. Any questions on that? Now what do I have to do?
Write them as a linear combination of vectors. S anyway.
Nah, not
Turn
quite.
it
What do
into
I
a matrix.
I'm looking for one very important word. I just showed they're linear independent. What else do I have to show?
Span.
Span. So we need to make sure we have our goal straight. Okay, to show that you have a basis, you have to show the linear independent, and you have to show they span. So I got linear independent. Now it's time to show they span. Does that make sense? So the nice thing about span, similar to linear independent, we have to show that every vector can be written as a linear combination of these three. And every vector in P3 looks like A plus X. BX plus CX squared. Any questions on that? Okay, by the way, it might bother you that I'm writing it in ascending order. Do you know why I am? Any guess? Instead of descending, which you learn in algebra. Okay, the reason is ascending is more important for higher level stuff. And that's because of power series. Power series are always written in ascending order because you can't do descending for power series. So that's the main reason. The ascending is probably more useful, and it's better to get used to ascending order for higher level stuff. Okay, well, I could do the same thing, right? But I don't have zeros anymore. I have A, B, and C. Does this have a solution?
Yes.
Yeah. So in particular, the solution is C1 is A, C3 is C, so C2 must be B minus A, just by subtracting C1 from both sides. And there's a solution. I got it. We're done. So therefore, S spans P2. So what's the final conclusion?
This is a basis of P2. S is the basis of P2.
Yeah, S is a basis of P2. Any questions at all on this example? Okay. And if it's not, doesn't span, or if it's not linear independent, it's not a basis. So by the way, since you asked it a while back, if you look at 9.3.4, if we look at these four polynomials, is that a basis for P3?
No.
The answer is no, because we've showed that they were not linear independent. And if they're not linear independent, it's not a basis. Does that make sense? And it doesn't span either, but all you have to do is have one of them doesn't work, and then it's not a basis. Okay. Any questions at all on kind of the examples on showing something's a basis or showing something's not a basis? Okay, so here's a nice little theorem, pretty easy one. Hopefully you'll agree. If S is equal to V1 through Vk is linearly independent set such that each vector in S is in the span of V1 through Vn, then K must be less than N. Okay, I think it's less than, let me see, less than or equal to N. There we go. So K must be less than or equal to N. Okay, why must that be true? We're going to run into problems if you don't have that true. Any thoughts? I'll let you read through this.
I'm thinking span because too many vectors theorem.
Yeah, so too many vectors theorem. We've already had this. We had it for, but we only had it for vectors in Rn. But it's no different if it's in, whatever it's in. Okay, and the proof is exactly the same, actually. You just write it out. So it just says that if you have, you know, a 10-dimensional space, okay, you're not going to be able to find 11 vectors that are linearly independent. Is that clear? Is that obvious to y'all, or do you need to see a proof?
No, it makes sense.
I'm guessing you're okay with it because I've proven some things already. So it's a it's a nice theorem because it makes showing something's not linearly independent easier. So typically you use this in the converse of this. Okay, and so the converse says the opposite. So if you have k greater than n and s is in the span, then s is not linearly independent. Okay, and that's a little logic that if A implies B, then not B implies not A. You learned that at one point in your life? So that's the logic statement. Very important, and you use that. So this is mostly used in that converse, going backwards. So really contrapositive is how you usually say it. Sorry. Okay, now comes a really important theorem / definition. The book kind of does theorem and definition, but you can't really say the theorem unless you understand the definition. So I put it as both. And that is every basis of a vector space contains the same number of vectors. And that number is called the dimension of V. Okay. So for example, let's do some examples. So what's the dimension of P2? So let's see if you can tell me the dimension of P2.
Well, just 2.
Okay, if it's 2, then tell me a basis that has 2 vectors in it. Remember, these are second degree polynomials or lower.
X and X squared.
Okay, so X and X squared, is that a basis for P2? Let's try it. So try X and X squared. And let's see what happens. Okay, that means that every vector in P2 can be written as a linear combination of X and X squared, right? Can that be written as a linear combination? Can 1 minus 3x plus x squared be written as a linear combination of x and x squared?
No, we need a 1 over there.
Okay, so that one can't work. Does that make sense? So 2 is not the answer. Do you agree?
3, yeah, 3.
Yeah, the answer is 3. So instead, what should we try for the basis?
One higher than the dimension of the polynomial space.
I liked your very first word, 1. None of the rest of it. 1 x and x squared. Is that clear? Do you agree that's a basis for P2, that every polynomial can be written as a number times 1 plus a number times x plus a number times x squared? That every polynomial of degree 2 or less can be written that way?
Yeah.
Yeah, that's a basis. So the dimension is 3. Any questions on that? So the dimension of P2 is 3 because a basis is 1x and x squared. And I'll let you work it out that they're linearly independent and they span. Span I just said, but linear independence obvious also. Okay. Any questions on this example? Very important example.
Will it always be the case that it's going to be higher than what we were looking at before?
When you say it and looking at before, tell me, give me some details.
Like P2, a degree 2 of at least 2 polynomial.
Yeah, you could be more specific than that. What if I said, what about P3000? What's the dimension of P3000?
I'm going to guess 3001.
Exactly. Exactly. Because you're looking at a polynomial of degree 3000. And the basis will be 1x, x squared, x cubed, all the way up to x to the 3000. There's 3001 of those. So the same argument works. You just have to keep going until you get to the right number. So it'll always be, so in particular, in fact, I'll just call that number 2. I wasn't going to, but I'll do it anyway. And that is P n has dimension n plus 1. Any questions on that? All right, let me give you another example. How about M 3/4? Do you remember what M 3/4 means?
All the matrix that are 3x4 matrices.
Exactly. Matrices that have 3 rows and 4 columns. What's the dimension of M 3/4?
M4x5.
I'm looking for a number. A dimension is a number. Notice in the definition, this number is called a dimension. The dimension. So what is the dimension? Hopefully all of you can participate and tell me. What's the dimension of M 3/4?
5.
5. Not quite. Keep trying.
4.
No. All right. So maybe I need to work it out. Hearing some interesting guesses, and it's always fun to hear interesting guesses. But let's figure out what's going on here. So let's write a matrix, and I'm going to start making a basis. It'll take all day to do all of them, but you'll get the idea when I create one. So 3 rows, 4 columns. So I'm going to start with 1, and all the rest are zeros. Comma. Then I'm going to do 0, and then 1, and all the rest are zeros. Do you agree so far they're linearly independent, those two?
Yeah.
Yeah? What do you think the next one's going to be?
0, 1, 0, 0, 1.
0, 0, 1. And now I hope you get the idea. Dot, dot, dot. How many am I going to need?
$12.
12. So M 3/4 has dimension 12. Because I need to make sure that I take care of all 12 of the entries. Any questions on that? Because if I miss any of the entries, then I didn't get it. And in fact, if you did this, you'd end up with a 12 by 12 matrix. If you didn't have a 12 by 12 matrix, you have no chance of it being non-singular. So this has dimension 12. How about M 7 by 8?
56.
Yeah, that'll have dimension 56. So the nice thing is that the dimension of the vector space of matrices that are M by N is just Mn. Any questions on these examples? How about the set of all differentiable functions? What's the dimension of the set of all differentiable functions?
Wouldn't it be infinity?
Yeah, this one's infinity. How would you prove it? I'm not going to prove it because it's kind of a bit long, but not too terrible. How would you prove it?
Maybe with a limit?
Eventually with a limit, but how would you start? What are you going to take a limit of, in other words?
We'll need to make sure that they are infinity linear independent vectors.
Yeah, and which one's you going to use? It's got to be in here somewhere. Oh, not operators. I see. How about basic? There it is. Infinity. So the dimension's infinity. And the reason is power series. So you can look at 1, x squared. Do you agree those are linearly independent?
Yeah.
And x cubed? Do you agree that we're still linearly independent?
Yeah.
And x to the 4th, and x to the 5th, and x to the 6th, still linearly independent? How far can I go?
Forever.
Exactly, and that's why the dimension's infinity. Because if the dimension was a finite number, then you can write down all those powers of x, and then you're going to have a linearly independent set with more vectors than the dimension, and that's not possible. So that's the proof in words, at least. So the set of all differential functions has dimension infinity. And by the way, if I change differentiable to continuous, that's still infinity. If I just drop differentiable, it's still infinity. So those are harder to work with, by the way. Good luck writing a basis. If it has dimension infinity, there is no basis. Any questions on that? Okay, so those are a bunch of examples of the dimensions of a vector space. Okay, just a note, since we did it, it's always nice since I've got it here. How about the dimension? How about the vector space that's a span of these 4 vectors? What is the dimension of this vector space?
4.
You sure?
It's
It's 2. It's 2 because when we RREF'd, we realized that only the first 2 were needed. Do you remember that? The other 2 could be written as linear combinations of the first 2. So the dimension of this vector space is 2. Any questions on that? Because the first 2 vectors or polynomials form a basis for this span. And that we did all the work, so I figured I can go back to it. Any questions so far? So again, it should feel familiar. It should feel similar. to what we've been doing all quarter, except our spaces are not just Rn, they're polynomials or matrices or functions. Lots of different kinds of vector spaces. Okay, next theorem. Let W be a non-zero subspace of a vector space V of dimension n. Then W has a basis with at most n vectors. If the basis for W has n vectors, then W is actually equal to V. So I'm going to let you look at this for a moment because I read it pretty fast. Make sure you can follow what's going on here. Okay, any questions before I kind of go through this? Okay, so let me do an example. Again, I could prove it, but I've found that if I prove everything, then all I get to do is prove, and then you don't understand anything because you've seen no examples. I think examples are important. So let me do an example, and let's let W be the following. So it's W equal the set 1 minus x plus x squared, comma, x plus x squared, comma, 1 minus x squared, comma, 1 plus x, comma, 2x plus 3x squared, and I guess I should write span. So let's say it's a span of those vectors. Okay. So let me ask you, can W can that be a basis for W? Can those vectors be a basis for W?
Well, if they are linearly independent, they can.
Okay, I want you to think, and the hint is read the theorem above. Read the theorem above. Can those 1, 2, 3, 4, 5 vectors be a basis for W? Let me write that down. What do you think?
Probably no.
The key is identify V. What's
Yeah,
V?
B it's P2, right?
Yeah. So note that V equals P2.
So W can have at most 3 vectors.
Yeah. So V is equal to P2, which has dimension 3, because I just showed that a moment ago. So W cannot have a basis with 5 vectors, since 5 is greater than 3. So we know that those 5 vectors cannot be a basis for W because W sits in P3. Is that totally clear? Okay, again, I think the example is a lot more enlightening than the proof, actually. You got to see what the point is, and this is the point. The point is you want to identify if you have a chance of being a basis. So the first thing, because it's really easy, is you just count how many there are. And if there's more than the space that it's sitting in this case, P2, then the answer is no. Okay, if it's less than the space it's sitting in, does that mean it's a basis?
No, it's not a basis.
No, it might be a basis, but it might not. So if you have, if it was a span of, say, 2 polynomials, it may or may not be a basis of W. Not a P2, of W. Okay, because they may not be linearly independent. They can be multiples of each other, for example. Any questions on that? Any questions on this theorem? Okay, so that's how you use it. Now comes the next theorem. Okay, so let V be the span of V1 through Vk. Okay, then there exists a subset of V that is a basis for V. Okay, I like to think of this as the kick it out theorem. Okay, so if V is a span of V1 through Vk, that means that if I'm allowed to kick out some vectors from that list, and I choose the right vectors to kick out, I'll get to a basis. Does that make sense? So it's a subset. It might not be all of them, but it means that you can eventually get to a basis. Okay, and then if W is V1 through VR, is a linearly independent subset of V, then W can be expanded to create a basis for V. Okay, so whereas that first sentence is kind of the kick out theorem, the second is the add them in theorem. Okay, so if we started with a linear independent set and it's a subset of V, it means that I can go find more vectors and get a basis of V. Where have you seen the second sentence today?
It's the above theorem, right?
Where have you seen an example of the second sentence?
The homework question I asked you.
Exactly. Let me scroll back up so we can see that happening. That's what we did. So the homework question. So what we had is, oh, sorry, the first one, not the second one. That was the first one. The homework question was the first sentence. So we have the span of these bunch of vectors. And what we needed to do is we need to kick out vectors until we got a basis. Does that make sense? And we kicked out the second and we kicked out the third and we got a basis. Then after that, we said, well, we could take the first two, and that's not a basis for P3, but now we can kind of add them in, add a couple extras, 1 and X, and get a basis for B. As long as you start with linear independent, you can add more in and eventually get a basis. Do you see how we did both of those in this example? Any questions on that idea? Okay, let me give you another example so we can see more, since we got some time still. Okay, let's suppose instead we're going to be looking at V is equal to the span of these matrices. Guess I need to go that guy, bracket. So the first vector is going to be 1, 1, 0, 0. The second vector is going to be 2, 2, 0, 0. And the third vector is going to be 1, 1, 1, 1. Find a basis for V. Any questions on the question? Okay, and the key here is we can use the theorem, the kick-out theorem. So what's a basis?
The first and third vectors.
Yeah, so the first and third, notice the second vector is just a multiple of the first. So I can kick that one out. So a basis for V is, and what I can do is I can take my vector space and I can kick out that middle vector. And now notice I kicked one out, which I know did not reduce V because it can be written as a linear combination of the other two, in particular, the first one. How do I know just by looking at it that these are linearly independent?
There's no way you can write the second vector by the first.
Yeah, in particular, when you only have two vectors, do you remember the easy way?
They are not multiples of each other.
Yeah, they're not multiples of each other, and they're clearly not because a multiple of the first is still going to have zeros on the bottom. You're never going to get to the second. Is that clear? So these are linearly independent. So that means we have a basis, and we only kicked out linear combinations of the rest. As long as you're only kicking out linear combinations of the rest, you're not reducing V. Any questions on that example? Okay, so now the question is, I'm going to have you try it. Find a basis for M 2 by 2. That includes one, 1, 0, 0 and 1, 1, 1, 1. Let's see if you can do that. By the way, how many vectors are you going to need? How many matrices?
2 more.
Yeah, you need 4 because we know that the dimension of M 2 by 2 is 4 because 2 times 2 is 4. So see if you can find a basis that includes these two. Okay, and by the way, the theorem says that you can, at least in theory. The question is, do you understand linear algebra well enough to be able to figure it out? And let's see if you can do that. So let's see if you can put in the chat box the other two vectors that you need to add, or the other two matrices. And there's lots of right answers, by the way. So my hint is be easy on yourselves. Okay, 1 0 0 0 and 0 0 1 0. Okay, how do we check if it worked?
We need to make sure they are linearly independent.
Yeah, we need to make sure they're linearly independent. And the way you can do that, one of the nice things with matrices is you can expand this matrix out as a vector in R4. Because really a matrix is 4 numbers, right? And all that still works. So what I can do is I can draw a 4x4 matrix. So I'm going to do that. And what's nice is we have a lot of theorems that we can use. So I need to add a row and a column. Okay, so I'm going to start out with 1 1 0 0 and then 1 1 1 1. And let's try the others. 1 0 0 0 and 0 0 1 0. And how do I tell whether this works? Whether these are linear, whether R4 were linear independent or not?
REF it.
You could do that. But what's the easiest way?
Determinant?
Yeah, I take the determinant, and I'm going to do a couple things. One, I'm going to partially RREF and then take the determinant. A little easier. So I'm going to reduce it a little, and that means I can take this 1 here, and I can make the ones above it a 0. Do you agree? And I can take this 1 here, make above that one a 0. And then it's much easier. Because now when I take the determinant, I'm going to have 1 times the determinant what's left. Then I can expand by this guy. That's another times 1 or -1. I don't care. Let's see. It's positive, negative, positive, negative, positive, negative. Yeah, it'll be -1. But all I care if it's not 0 or not. Times what's left. And then you're just going to have the 1, 0, 1, 1. That has determinant 1. So this has determinant -1, and that's non-zero. So it has non-zero determinant. So that means that we have a basis. Any questions on that? On that process? Okay, next. It's kind of weird. We're moving over to the next section. But hopefully you're used to it by now. Should you worry that we only have 10 minutes left for the next section and I just spent an hour and a half or whatever, maybe an hour and 10 minutes on the first section? Should you worry?
No, it's probably related.
It's not just related, but this book is like, sections are not the same length. This is a tiny section, just to let you know, whereas the first section is pretty long. So there's very little to say here. So here's the thing. Let V be a vector space and U and W be subspaces of V. You got the idea of what that means, at least, from the last section, what it means to be subspaces? Then U plus W is a set of all U plus W, such that U is in U and W is in W. Okay, it's kind of, in terms of the definition, it's what you would guess. And U intersection W is a set of all V such that V is in both U and W. Any questions on those two big definitions? So you could take a sum of two subspaces, and you could take an intersection of two subspaces. Any questions on that idea? Okay, if U intersection W equals 0, then U plus W is called the direct sum. This is just a definition. So it's just a special case of U and W. And we denote it in this special way. You put a circle around the plus sign. Don't get mad at me. I'm not the one that came up with this, but it's, it's what people do. And you write U direct sum W. And that's the same thing as U plus W, but in the special case where U and W have only trivial intersection. Okay, then comes a big theorem. And it says if V is a vector space with subspaces U and W, such that U and W both have finite dimension, then U plus W also has finite dimension. You're not going to get a finite dimensional vector space, add it to another finite dimensional vector space, and get an infinite one. That can't happen. But even more so, dimension of U plus W is the dimension of U plus the dimension of W minus the dimension of U intersection W. Any questions on the theorem? Okay, let me do an example. And this example has 4 parts. So let V equal the span of 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 0. And let's say W is a span of 1, 0, 0, 1 and 2, 0, 0, 2. So I have 4 questions and I want you to do them. First, find the dimension of V. Second, find the dimension of W. Third, find the direct sum of V and W. And the 4th question is, why will the above get you prepared for Sunday? So I'm going to give you a few minutes. See if you can answer, because I haven't had you try anything yet. Let's see if you could do A, B, and C. So I'll give you a few minutes. And D. D, you'll smile. It's guaranteed. So give it a try. Spend a couple minutes and see if you can work this out. Find the dimension of V. Find the dimension of W. Find the dimension of the direct sum of V and W. And then explain why will the above get you prepared for Sunday. And I spent a lot of time trying to come up with an example so that I could ask D. So when you have it, put it in the chat box. When you have them all. Or at least A, B, and C. So hopefully you're all working on it. If you have any questions, ask. All right, Victor, you got A and B right. Not C though. No, it's not. Yeah, Bradley's got it. All right, let's take a look at this since we only have another 2 minutes. So first, let's do A. How do we get the dimension of V?
The second vector is a linear combination.
Well, let's find out. How do you find out?
Oh wait, no, never mind. It's not.
You can make a matrix, and we can make it a 4, right? We can make it a 3 by 4 matrix, right? Any questions on that? In other words, you can write out, let me grab it. We can write 1, 0, 0, 0, 1, 1, 0, 0, and 1, 1, 1, 0. And we can find out the rank of this matrix. Does that make sense? Because the rank of the matrix will be the dimension of V, because that's how many of these you need to keep. But what's the rank of this matrix?
It's 3.
It's 3, right? Notice this is lower triangular. Okay, so this is 3. When you RREF, that becomes 0, that becomes 0, and that becomes 0. And then we have 3 pivot columns. So that means the rank is 3. So the dimension of V is equal to 3. How about B?
So the second vector is a linear combination of the first.
Yeah, and
So
hopefully
the-
that's obvious. 2 vectors are much easier than 3. Do you agree? So what is the dimension?
1.
Dimension has to be 1 because it's not 0 because the first vector is not the 0 vector. If the dimension is 0, that means you only have the 0 vector. But it can't be 2 because the second is a linear combination of the first. It's a multiple of it. Okay, then C, we can use a theorem if you want. What's the intersection of V and W?
I think it's 1.
It's not 1.
Or it's just 1, 0, 0, 1.
No. Notice, what do you notice about the fourth element, the 2, 2 element of all of vectors in V?
They're all 0.
They're all zeros. What about the vectors in W? Okay.
1.
They're not all zeros, right? Right. So that means W, this vector 1, 0, 0, 1 is not in the span of these 3. Is that clear? So that means the intersection has to have dimension 1. I mean, sorry, dimension 0. There is no intersection. Do you agree? So for C, we could take the dimension of U, which was, or dimension V in this case, which was 3 plus 1 minus 0. And what do you get?
4.
4. All right. Who got part D? Can you tell me? Sunday, that's a hint. This Sunday.
Is it Easter?
It's going to be on the homework, maybe?
No, it's the most important day in the entire world for us mathematicians.
Pi Day.
It's Pi Day.
Oh,
314. You don't know how long it took for me to come up with this. So Sunday is Pi Day.
did you do something special for your classes on the Pi Day that was on the in 2015?
Yeah, we made the national news.
Really?
Yeah. Yeah, we made the national news. Yeah, we had a big, huge event in Tahoe. Everyone came. It was actually on a weekend. And we went in and we had a big Pi Day celebration. We had like over 100 people. We had pie for everyone, and we did all kinds of fun pie stuff at the gondola. Yeah, and the news came, which was cool.
That
But
is
yeah,
really
so-
cool.
Yeah, we had a lot of fun, and it was great. So anyhow, we're out of time, but hopefully you understand what we did today. And again, that warning is it's the homework, the first half of the homework, the first section is from the book, and the second is just go to the Canvas and click on the syllabus, and you'll see the problems from that section that I created, because the book doesn't have any problems. I don't get it. So I'm going to stop the share, and I'm going to stop the recording.